Okay, so this is an example of Fourier analysis that I took from the Mathematica help page, essentially. So it's just, we didn't write this code, it's just taken right from their discrete Fourier analysis examples. So here I have a signal that's cosine of 30 times 2 pi over n divided by 200, plus a random real minus 1/2. So sine is going to go from -1 to 1.
Yep.
And I'm adding on random noise that's going from -1/2 to 1/2, and I get this. And it's not necessarily clear that there's a signal there, but maybe you would think that there was one. And when you do this Fourier analysis, you get these gigantic spikes which show you, hey, there's a signal there. But I can make this a little bit more complicated by saying, what if I had a lot more noise? So I'll do it 4 times the noise. So the noise is, instead of going from -1/2 to 1/2, is now going from -2 to 2. So it's actually bigger. The noise is bigger than the signal. So now you get something that looks like that. But the Fourier analysis still picks out that there's a signal there. These spikes are saying, hey, there's something there. Whereas if I make the signal 10 times the noise, multiplying this by 20, now it might be harder to find.
Well, I think that these were the original signals, but you can't tell anymore.
Right, so now it's hiding. But it's not too surprising. This is going from -10 to 10 up here. And it's just noise, and it's very hard to tell that there's a signal hiding in the noise. And you're right, these spikes that we saw before, like maybe here and here, were sort of signs that there was a signal there. But now the noise is so high, it's just kind of dwarfing it. So it's not like Fourier analysis can always pick out the signal out of randomness. But what you can do is, well, actually, let me ask you, what do you think you could do if you were trying to collect data that was really noisy, but you were pretty sure had a signal in it? So here I've collected 200 data points.
You could collect more data.
All right, so maybe 10 times as much. So I get 10 times as much data. Now it's not showing up. It just looks like it's just random numbers between -10 and 10. But now when I do the Fourier analysis,
you can see again that you have a signal.
I'm starting to get a hint that maybe there in fact is a signal there. Now these spikes are much higher than the other ones. And if I did something crazy, like I was able to collect, originally we were doing 200 data points, and now I'm doing 100 times that. And now it just looks completely, I mean, obviously this is all kind of smushed together, but it really just looks completely like noise visually. But now the Fourier analysis is telling you what?
It's telling us there's a signal.
Yeah, there's absolutely a signal there. Now, I'll do one last thing to show you kind of how neat this is. Let's go back down to 200. So you can't really tell. But let's put in a second signal. Sine of 10 times. So it's happening at a totally different frequency. Actually, I'll make it 11 times so they don't even accidentally overlap until a long time. Okay, so that's what that looks like.
We still have a large amount of noise.
Yeah. Now there's 2 signals and you can't tell. But if I go back to, if I'm able to go to 10 times as much data,
still you can.
I'm starting to see some spikes. And if I have 100 times as much data, oops, sorry about that, I gotta scroll up even more. I see the spikes very clearly. So, and this is, again, this is basically the same idea as that you're seeing in Cramer's rule. Out of the output, the B's, or the data you're collecting here, which is very noisy, there are amazing mathematical techniques that pull out the signals. And they just use basic concepts in linear algebra or basic concepts in calculus. And these are very powerful techniques that are around you all the time. Like are, again, the cable or the internet or the telephones pulling out these signals. So it's really cool. All right, good job this morning, then.